Oh yes, hello. My name's Edwin Walsh. Like I said, I work for the Center for Care Technology from the University of Antwerpen, and I'd like to talk about the optical head post tracking sensor using an infrared LED-based markers and a low-cost camera. It will be a bit less impressive as the previous talk, but hopefully you'll still find it quite interesting. But before I start, first let me tell you about this project came to be. It's the Center for Care Technology is an interfacultary center that aims to close the gap between the industry, the healthcare sector, research centers, university, and society. This is done, for example, by involving all of the stakeholders when we're trying to research new applications. And it's through this involvement of the stakeholders that we receive new requests to look into alternative solutions. And one of these requests was made to research the alternative input devices for people with limited hand control or arm movement. When such a request is received by us, we usually start by researching the current state of the art based on literature studies, but also with interviews from industry experts and interviews with actual users. So what are the current alternatives for the device that we propose? It can be divided into 4 subcategories, either switch or joystick-oriented devices, head tracking devices, head post tracking devices, it's using multiple markers, and gaze tracking systems. It's very hard to give an actual overview of all of the problems that you have with these solutions, so keep in mind that I will simplify them in this presentation. But with switch and joystick-oriented devices, they come in many forms, like tongue-driven switches or accelerometer-driven switches, even through brain computing interfaces. But the biggest issue with these devices is that they're perceived as slow. They're quite often very intrusive and very stigmatizing. A less intrusive system is the single marker head tracking system. The general principle is that a marker on the head is tracked. That can be either a feature in the face, the nose, or some marker placed on the head. And then the relative movement of this marker is translated into movement of the mouse pointer. But the main issue with this system is that after a while, the pointer will drift off to the side of the screen. And then you need to do a very big corrective motion to get your mouse pointer back into an actual correct position. It's the need for this corrective motion that's often seen as a very big disadvantage of the system. With head post tracking, it overcomes this problem by using multiple markers to actually track the location of the head and the rotation of the head relative to the screen. And based on the head pose, the point on the screen where the head is pointing at can be estimated. The advantage of this system is that it can be produced at relatively low cost, and it requires no calibration. The low cost issue is something that will continue to come back in the presentation. The 4th solution is our gaze tracking solutions. The process is calculating the exact point where a person is looking at. There's many different ways to implement this. There's several commercial eye gaze systems available. Most of them are still quite expensive, and they require the user to actually be close to the camera. And although a lot of research has been done to make them low cost, there's still quite a lot of issues with them, either through low accuracy or they're very CPU intensive. It can also be very highly stigmatizing. And in spite of the high amount of research done into gaze tracking systems, there's still some disadvantages to using eye gaze as an input device. For example, it's not clear whether you're actually inputting a command or if you're just trying to look at something. That's called the Midas touch effect. And another issue is that you have due to the saccadic motion of your eyes, it's very hard to actually draw smooth lines using your eyes. You can only jump from one place to the other. So what solution do we propose? We're based on a cheap infrared sensitive camera. Again, saying it's cheap, it's very important that we can make stuff which is affordable with off-the-shelf products, because it's a very small target group and they cannot afford the high prices that it otherwise would cost. We mount them on a pair of glasses and we use infrared markers placed around the screen. With infrared sensitive camera, I mean it's near infrared. It's actually a normal off-the-shelf camera where the infrared filter has been removed. And having one wearable controller gives a and multiple markers gives an additional benefit that it makes it easy to do some environmental control. By just adding a couple of markers around the area, you can easily turn on a light switch or open the curtains just by looking or pointing your head at the right direction. But making a wearable device does lead to some challenging constraints. It needs to be wearable, needs to be usable for a long period of time. That leads to some very limited processing power. This is the main reason why we use with the infrared markers, as you can see in the center image at the bottom, by using an infrared bandpass filter. And in this case, we just used the cutout of an old floppy drive. It's very easy to make a black and white image that just shows the blobs from the different LEDs. And through some very simple calculations, you can get, you can do the blob detection and filter out the locations of your LEDs using very little processing power. So we built a prototype to validate this proposal. We used the Raspberry Pi with the no infrared camera module and a couple of 850 nanometers infrared LEDs. These are things that are very easily available, which make it a very cheap prototype. And then, as mentioned, we used the cutout from the floppy disk as an infrared bandpass filter. This obviously isn't a very, very good filter, but even with these simple things, we can get quite decent results. We then estimate where the camera is pointing at using a homography matrix. Main principle behind a homography matrix is that any two images in the same planar surface in space, they are related by a homography. And this homography matrix can be estimated, for example, by using the direct linear transformation as it's discussed by Hartley and Sisselman. We then place the camera on a pan-tilt system and taught the system to point the camera at 1,600 points on the screen, then use our system to calculate the mouse coordinates 10 times for each of these 1,600 points. And then the bottom left image shows the mean error vector for each position on the screen. So the error direction changes very smoothly in respect to the cursor, which is desirable for smooth interaction of the mouse. The mean absolute size is about 12 pixels, which isn't very big, but it's not as good as we would hope. But a more important result is when we check at the standard deviation, which you can see in the image on the right. It's a histogram of the standard deviation, pointing the image at one location and then doing phased measurements for that one location. And we get a standard deviation of about, well, it's lower than 2 pixels, which means that when the sensor is in place on an immobile object, hardly any movement of the cursor will be detected. But due to the small standard deviation, it's expected that people will be able to automatically correct for the mean error that we see in the left-hand side image. A large standard deviation would cause a big jitter on the mouse pointer. So the previous tests led us to believe that the system is accurate enough to be used by people. Performed some preliminary tests on 4 healthy users by placing the Raspberry Pi camera on a pair of glasses. But to validate the performance of our device on these actual users, we used a multiple direction tapping test. As you can see on the top left image, it's described in the ISO 9241-411 specification. And the idea is that the user needs to select first the top circle, then go down, then go up again, and go through the entire outer circle by selecting all of the inner circles. In this way, you can simulate actual mouse movement in an independent way of the type of device. So yeah, the users need to select varying target widths or the varying distance, and then based on the difficulty of this test, which is based on how large are the circles, how much distance do they need to perform, you get a throughput value, which is this independent value on which we can compare different devices. The second column of the images show the results from these healthy users performing the test with a traditional mouse. And the third column shows the results from the head post tracking system. The top image is a box plot of the throughput for the 12 users, for the 12 tests that the users performed. Then the bottom image is a 2D kernel density estimate of the normalized cursor position for a single user, accumulated over all the 12 trials, which is quite a mouthful and basically just means it's a trace of the movements that the user performed with their mouse. So there's some interesting things that we can see. Well, first of all, on the box plots, you can't really tell from this image, but the results that you see, they are very similar to other state-of-the-art input devices like eye gaze systems and other tracking systems. But mainly in the density estimates, you can see the left-hand side is really the case that we want to get at. This is with people that have experience with using their mouse, so they go to those positions very quickly, very clearly. They use it very efficiently. You can see that all of the dots at the outer circle, they're very, very centered. And you can also still vaguely make out the lines that the person has done over these 12 trials, which means that each of these 12 trials, they actually do almost exactly the same path to get to the same solution. On the right-hand side, you can see that it's not as good as when people use their actual mouse, but you can still tell that it's very small blobs where they have selected their object. So it is quite accurate, and you can still vaguely detect what they have done, but there is obviously room for improvement. So from these images, we conclude that there is room for improvement, but the preliminary test results give us throughput values which are comparable to other state-of-the-art. So it's clear from the experimental results that the proposed system using infrared LEDs and the cheap infrared sensitive camera provides sufficient accuracy and consistency when placed on an immovable object. And further tests with untrained subject users have showed that the proposed solution achieves throughput rates similar to other state-of-the-art solutions. There is, however, a lot of room for improvement, for improving the quality and ease of use of the sensor. And in future work, we will concentrate on implementing an intelligent and adaptive tremor suppression, which is expected to lead to even better results. This is, we noticed with the users that when they actually try to hold their head still, the mouse pointer still moves quite a bit. We proved from the immovable object that it isn't due to our sensor, so that it is due to actual movement of the head. So that are filters that we need to try and filter out the actual tremor of the person to be able to get the smooth results. It's also expected that gaining experience with the system will have a very large impact on the performance, so further studies will be performed through extensive user testing to gain more insight on the learning curve and how this learning process can be optimized. Also, the initial tests were performed in laboratory conditions with controlled lighting, so additional experiments will be performed to analyze the potential influence of heavy sunlight, which could lead to high level of noise in the camera image. Then to provide a true wearable device, we must perform miniaturization of the hardware, and we'll follow a model-driven approach to continuously reduce the power consumption of the device while still maintaining sufficient performance to allow for smooth operation. And lastly, we will implement the detection of the multiple markers so that multiple devices can be controlled with the same controller, and that it enables environmental control. So finally, I'd like to thank you for your attention, and are there any questions?